Recall that we say that y varies at a constant rate of change of m with respect to x if the changes in x and y are proportional, which means that the ratio of the change in y to the change in x is always equal to some constant number m, which also means that the change in y is always m times as large as the corresponding change in x. And this number m is constant no matter what pair of changes of x and y we look at. So let's look at a specific example. We'll assume y varies at a constant rate of change with respect to x, and the change in y is always -3 times as large as the change in x. And we'll assume that y equals 7 when x equals 4. Now, this information right here is enough for us to determine the value of y given any value of x. So for example, when x equals 6, we can imagine x changing from an initial value of 4 to a final value of 6. And this change in x is equal to 6 minus 4, which equals 2. Now, given the constant rate of change of -3, we know that the change in y has to be -3 times as large as the change in x. So the change in y is -3 times 2, which equals -6. Therefore, when x equals 6, y is equal to the initial value of y, which is 7, plus however much y changed by. So the value of y when x equals 6 is 7 plus -6, which is equal to 1. So when x equals 6, y equals 1. Now we can use this way of thinking to actually determine new values of y given any constant rate of change, m, and if we have any reference point for x and y. So let's assume y varies at a constant rate of change of m with respect to x, and we'll assume that y equals y1 when x equals x1. So we'll just plot some arbitrary values for x1, so we'll assume x1 is right here, maybe y1 is right here. So we have a reference point, x1, y1, and y varies at a constant rate of change of m with respect to x. So this means that if we pick any value of x, so any new value of x, we can imagine x changing from a reference value of x1 to its new final value. We know that this change in x has to be equal to x minus x1. And given the constant rate of change of m, we know that the change in y, so the change in y, is m times as large as this change in x. So the change in y is m times delta x, and delta x is equal to x minus x1. Now the new value of y, which is about right here, is equal to, so this value of y is equal to the initial value of y, y1, plus the change in y. So plus delta y, or we could rewrite this as the change in y plus the initial value of y. And we know that the change in y is equal to m times x minus x1, x minus x1 plus y1. So if we take all of this information, we decided that for any value of x, y is equal to m times x minus x1 plus y1. Now this right here, we can use this formula that expresses y in terms of x given any constant rate of change m and any reference values for x and y, which we used x1 and y1. We call this form the general linear function formula. So this is a formula that will let us express y in terms of x for any linear function. Now, with this linear function formula, we know what each piece represents. So in the formula, y equals m times x minus x1 plus y1. We can break this down into individual pieces. We know that x1 represents the reference value, so the reference value for x. Then x minus x1 represents the change in x. So the change in x from x1, so from x1 to the current value of x. Then when we multiply that change in x by m, that tells us the change in y. So then if we take the change in y and we add that to the reference value of y, the whole expression represents the new value of y. So we can construct this general linear function formula, and we can also look at one and decide what each piece represents. So let's look at an example with some numbers. Let's assume x and y vary together such that y equals 2 times x minus 5 plus 1. Let's decide how x and y vary together and pick out some information that we know. Now this formula expressing y in terms of x is in the general linear function formula form. So we can look and see that x minus 5 tells us that 5 is the reference value for x. So 5 is the reference value for x. We also know that since we have this plus 1, 1 is going to be a reference value for y. And then we also know that this 2 represents the constant rate of change of y with respect to x. So this 2 tells us that the change in y is 2 times as large as the change in x. So we have a reference point of 5, 1, and we know that the constant rate of change of y with respect to x is 2. Now given any value of x, we can engage in the reasoning we did before, or we can use our formula and think about what each step represents. So let's assume that, let's use a new color. So let's say x equals 3.5. We can compute y by plugging 3.5 into our formula. So y equals 2 times 3.5 minus 5 plus 1. Now, we can compute this value and we'll get a number, but we can actually think about what each piece represents. 3.5 minus 5 represents the change in x if we started at 5 and we ended at 3.5. And this has a value of negative 1.5. So this is like a change in x. And if we multiply that change in x by 2, multiply that by 2, we're going to get the change in y. So however much y changes by as x changes from 5 to 3.5. Then, if we add 1 to that, which is our reference value, we're going to get the new value of y. So if we take the change in y, and we add our reference value of y, when we add 1, we'll get our new value for y. Now, this expression has a value of 2 times negative 1.5 plus 1, which is equal to negative 3 plus 1, which is equal to negative 2. So when x equals 3.5, y is equal to negative 2. Now, if we imagine using this way of thinking and allow x to vary, we can actually think about tracing out all points x, y that are in this relationship. So if we imagine tracing that point x, y as x and y vary together, what we get is the graph of y in terms of x.